What if the future of timekeeping didn't come from a billion-dollar lab invention, but from a trick jewelers have used for over 200 years? For decades, scientists have chased a radical idea: a nuclear clock. Unlike today's atomic clocks, which rely on electrons, nuclear clocks use the nucleus of an atom itself. That makes them far more stable, more precise, and far less sensitive to environmental noise. In theory, they could redefine navigation, communications, and even how we test the laws of physics. Last year, a team led by UCLA reached a milestone scientists had been pursuing for nearly half a century. They successfully made radioactive thorium-229 nuclei interact with light, absorbing and emitting photons the way electrons do in ordinary atoms. First proposed back in 2008, this breakthrough opened the door to clocks so precise they could detect tiny shifts in fundamental constants of nature. But there was a huge problem. Thorium-229 is incredibly rare. It only exists as a byproduct of weapons-grade uranium, and researchers estimate that just 40 grams are available worldwide for nuclear clock research. Early experiments required at least a milligram at a time, an enormous amount given how scarce the material is. Now, a new study published in Nature shows a way around that limitation, and the solution is surprisingly simple. Instead of growing fragile, hard-to-make thorium-doped crystals, UCLA physicist Eric Hudson and his international team used electroplating. The same basic technique used to coat jewelry with gold or silver. By slightly modifying this centuries-old industrial process, they deposited an ultra-thin layer of thorium onto stainless steel. The result? The same nuclear behavior, using 1,000 times less thorium. For years, researchers assumed thorium had to be embedded in transparent crystals so laser light could reach the nucleus. But that assumption turned out to be wrong. Hudson's team realized that enough laser light can penetrate opaque materials to excite nuclei near the surface. And instead of emitting photons, those excited nuclei release electrons, which can be detected simply by measuring an electrical current. In other words, one of the hardest problems in nuclear physics was solved with one of the easiest measurements in the lab. The implications are enormous. This approach could make nuclear clocks smaller, tougher, and far more affordable, potentially compact enough for phones, wristwatches, power grids, cell towers, and GPS satellites. Even more importantly, thorium-based nuclear clocks could enable satellite-free navigation, critical for submarines, deep space missions, and scenarios where GPS is disrupted or unavailable. Scientists believe these clocks could also revolutionize fundamental physics, allowing ultra-precise tests of Einstein's theory of relativity and helping establish a solar system-wide time standard for future space exploration. After 15 years of painstaking crystal growth, the breakthrough came from rethinking a single assumption and borrowing a trick straight from an old jeweler's workshop. Sometimes the future doesn't arrive with something new. It arrives when we finally realize we were making it harder than it ever needed to be.